Hello, our topic today is fluid maintenance. If you are a student, a service technician, a salesman, or an engineer new to fluid power, or you are someone looking for a better understanding of maintaining fluid powered systems, this lesson is for you. I will cover a broad range of subjects and there will be opportunities to answer questions at the end. Our training goals for today are to present a broad overview of fluid maintenance, to explain the need for filtration in both pneumatic and hydraulic systems, to detail areas of need for pneumatic and hydraulic systems, to discuss critical components in hydraulic and pneumatic systems, and to introduce best practices for maintaining hydraulic and pneumatic systems. Fluids that are not regularly cleaned collect microscopic particles that accumulate and cause faulty operation and damage. Our conversation will start with maintenance of hydraulic fluid. Hydraulic fluid is relatively easy to maintain with a competent maintenance program that includes regular service and monitoring. There are many ways to identify the type of maintenance a company practices, but no matter what it is called, it will generally fall into one of the names here. Regular service falls under a plan called routine or preventative maintenance. There is a form of maintenance plan called predictive maintenance, which is a form of maintenance that practices the repair or replacing of key components before they wear out, thus, in theory, eliminating a breakdown before it happens. Some companies, unfortunately, do not prioritize preventative maintenance and suffer a pattern of abuse called reactive maintenance. We will begin by discussing the origin and nature of contamination along with its effect on system operation. Hydraulic oil circulates through the system, contacting the surfaces of all moving parts, providing lubrication as well as other functions. It only stands to reason that contamination in the form of surface wear, pollutants, and degradation of the oil will occur. When a failure does happen, it is critical that the hydraulic system be thoroughly cleaned so that any residual contamination does not cause repeat failure. Any failure of the pump requires that the system be flushed, valves removed from their mounting locations, and compressed air used to remove tiny particles. 80% of all machine failures, regardless of type, can be attributed to contaminated fluid. During manufacture, contaminants such as weld slag, metal chips from drilling, as well as rust, paint chips, and greases may accumulate in the reservoir and be circulated through the system. It has been observed that the practice of some shops is to collect oil leaking from a machine and reuse it. Exposed to the atmosphere, oil absorbs numerous types of contaminants and therefore should not be reused. In some cases, the wiper seals on a cylinder may be defective and dirt may enter the system because the seals are no longer wiping the rod clean. Another contaminant source, component wear, is normal but creates very hard particles which may accumulate and produce abrasive compounds, accelerating wear on sensitive machine surfaces. By controlling the level of contaminants to acceptable levels, you can eliminate as much as 75% of the potential causes of system failure. This is extremely important when you consider high equipment cost and our dependence on today's sophisticated and complex hydraulic fluid power systems. The reason dirt plays a large role in system inefficiency is simple. Dirt behaves like minute abrasive gravel, which travels through a system and internally deteriorates and destroys sensitive hydraulic components, causing reduced efficiency and eventually system failure. Dirt causes surface scoring, produced when abrasive particles flow across contact surfaces of hydraulic seals. Clearance honing, from dirt flowing through spaces between moving parts, creating greater clearances and destroying critical tolerances. Fluid degradation. Fine metallic particles act as a catalyst promoting the chemical breakdown of your fluid. Internal leakage or slippage, lowering the efficiency of pumps, motors, and cylinders, wasting power and increasing heat. Valves cannot control flow and pressure accurately. Corrosion, damage to delicate components, parts from fluid degradation, and sticking parts, causing erratic or intermittent component operation. These are the most common types of contaminants. Solid contaminants represent particles which do not dissolve and or have abrasive effect on metal surfaces. Liquid contamination may be water or chemical. Gaseous contamination is usually in the form of air in the oil. Heat can accelerate oxidation, leading to other forms of contamination. The majority of heat generated by the hydraulic system is dissipated at the reservoir. The amount of heat produced is a product of the system's working pressure and the flow generated by the pump. For every 1 horsepower developed by the system, 2,544 BTUs of heat energy are produced. The bottom line, the more horsepower a machine can make, the more heat it can generate. The most important job of the reservoir is to shed more heat than what can build up, otherwise the system may overheat. To a large degree, the hydraulic machine's ability to manage its heat is determined by its fluid capacity. The starting point is sizing the tank to at least 3 times the rated flow of the pump. The major function of hydraulic fluid is to provide energy transmission through the system, which enables work and motion to be accomplished. Hydraulic fluids are also responsible for lubrication, heat transfer, and contamination control. So it's a lube and a power transfer device. This dual role makes it unique. To be an effective and reliable lubricant, hydraulic oil must possess properties similar to most other lubricants. These include foaming resistance and air release, thermal, oxidation, and hydrolytic stability, which is the ability of the lubricant and its additives to resist chemical decomposition in the presence of water, anti-wear performance, filterability, demulsibility, which is the ability to release water, rust and corrosion inhibition, and viscosity in respect of its influence on film thickness. When oil contacts a surface, it forms a strong molecular barrier. To be most efficient in its role as a power transfer device, hydraulic oil needs high bulk modulus, which is high resistance to reduction in volume under pressure, and high viscosity index, which is the low rate of change in viscosity with temperature. Most hydraulic reservoirs are manufactured from steel, stainless steel, or aluminum. But another option is aluminized steel. The use of aluminized steel, which is sheet steel, hot dip coated on both sides with aluminum and silicone alloy, solves the contamination problems inherent in uncoated steels. Built according to current standards, reservoirs come with a number of features. See the different features on this slide. The JIC style reservoir is an industry standard welded top tank that comes with 2 removable end covers on opposing ends. The removable end covers allow you to access internal plumbing and components for assembly and repair, but also allows for easy clean out when the reservoir is empty. Reservoir capacity at number 1 should be 3 times the rated flow of the pump and should be permanently marked on the top plate. The mounting plate at number 2 facilitates a secure surface for mounting the prime mover. The flexible motor coupling at number 3 connects prime mover to the hydraulic pump and allows for variances in alignment. The filler breather cap at number 4 allows for adding of fluid, escape or entry of air, and filtration of air. The baffle at number 5 forces return fluid to travel further before returning to the suction to ensure greater fallout of contamination and escape of air. The reservoir legs at number 6 allow for the mounting and circulation of air. Additional return and drain lines at number 7 allow for machine modifications. The oil level indicator at number 8 is to allow monitoring of the fluid level. Cleanout covers at number 9 allow easy access for removal of contamination. The drain plug at number 10 allows for draining prior to cover removal. The reservoir tank itself at number 11 holds fluid and acts as a conduit by which heat escapes to the surrounding air. Material of the tank is usually SAE 1020 steel, but it could also be aluminum or aluminized steel. And these are major benefits when you consider the need for heat transfer. The reservoir style you choose will be based on price and available space. You should choose the largest reservoir money and space will allow, and if possible, the tank should permit flooded suction. Flooded suction occurs when the pump inlet port is below the oil level, either inside or outside the reservoir. L-shaped, T-shaped, and elevated reservoirs provide the best combination of attributes, but are large and costly. Components are typically welded or mounted to the top of JIC reservoirs, such as pump and motor groups, filters, heat exchangers. You can also mount a JIC reservoir on an elevated platform, which provides the below-mounted components with flooded suction and ease of access. Be aware that leaks in above component tank designs are exacerbated by gravity. These are symbols for coolers used in hydraulic systems. Heat kills hydraulic systems. That's why hydraulic oil coolers are widely used in a diverse range of agricultural, mobile, manufacturing, and industrial settings. They remove excess heat generated by energy losses in a system, as well as that from external sources such as engines, furnaces, and even the surrounding environment. In fact, coolers are often essential for designing temperature-optimized hydraulic systems that keep oil temperatures within a limited range. Such circuits are basic prerequisites for cost-efficient operation, as they provide a number of performance, economic, and environmental benefits. Maintaining the correct temperature keeps oil at its recommended viscosity, ensuring mechanical components are properly lubricated and hydraulic devices run at peak efficiency. Letting oil temperature rise beyond recommended limits can reduce the life of a system due to poor lubrication, higher internal leakage, a higher risk of cavitation, and damaged components. Air-cooled systems dissipate heat with flowing air. This type of cooler operates by forcing cold air over hot fluid inside a heat exchanger's coil or core. Low running cost and simple maintenance are attractive benefits of air-cooled systems. They also eliminate water contamination problems and minimize corrosion. Additionally, heat generated from air-cooled systems can be used for other purposes. On the downside, the upfront expense of an air-cooled system exceeds that of a water-cooled unit. Air-based versions are also larger and generate more noise, so that they can degrade the work environment. What's more, these coolers require ventilation and clean air, and variations in ambient temperature can greatly affect cooling capacity, making steady-state operation more difficult to maintain. Water-cooled systems use cold water to remove heat, with hot and cold fluids separated by a barrier. Compared to air-cooled systems of equivalent capacity, water-cooled systems have lower upfront costs. They also are quiet, they're compact, and do not alter the surrounding ambient temperature. Variations in air temperature have little or no effect on cooling capacity, which allows for greater consistency. Meanwhile, the system's heated water can be used for other on-site purposes. The construction of most coolers requires that they be located in the return line to the reservoir. In addition to low pressure operation, they must be protected from clogging by use of a bypass check valve. The check valve ensures that oil flow to the reservoir will not be interrupted. The basic schematic symbol for a filter or strainer is the same whether it is hydraulic or pneumatic. On the right, the schematic symbol of a filter with a bypass check valve is shown. As the filter becomes restrictive due to particle buildup, the pressure difference across the check valve will increase until the spring tension is reached. When differential reaches the spring tension, about 25 psi, the check valve will unseat and the oil will move unfiltered around the media. When this happens, the filter is said to be in bypass. It supposes that dirty oil is preferred over no oil. In reality, most filters would rupture without a bypass mechanism. Pictured are three typical filter designs: a coarse filtering strainer, a high pressure filter, and a low pressure spin-on filter. The primary difference between filters and strainers is in the size of the particles that they are removing. In simpler terms, the word strainer is typically used if the particulate being removed is visible to the naked eye, around 40 microns, whereas if the particulate is too small to see with the naked eye, generally below 40 microns, the term filter is used. This circuit shows where different types of filters are located. In the reservoir, you would normally have a strainer at location number 1 with a bypass check valve. Right above the pump at location number 2, you would have a pressure filter without a bypass. The pressure filter protects the proportional valve controlling the motor. Below the DCV on the right at point 3, you have a return line filter, and number 4, which is protected by a bypass check valve. On the lower right side of the drawing is an offline kidney loop filtration system. On the very lower right side of the reservoir is the symbol for a filler breather cap that also has a filter element to clean the air that enters the reservoir. The kidney loop system takes oil out of the reservoir and cleans it, whether the machine is running or not. This system can be part of the machine, added later to an existing machine, or placed on a dolly and moved from machine to machine as needed. Many fluid power vendors rent them, but they are not difficult to build. As mentioned before, they can filter the oil of the machine whether it is running or not. This system can extend the life of the oil in some applications and even pay for itself with the savings. Particle counters can accurately measure and count very small particles and relay that information to a printout. This is especially useful as human vision is limited to about 40 microns or larger. This type of analysis is considered very sophisticated and reliable. Particle counters can determine what the particle is, which in turn can lead to the prevention of a major failure. If, let's say, there are very hard particles of nickel in the oil, this could identify the progress of a bearing failure. Often, the material the contaminant is made of gives a clue as to where it came from. Anyone involved with the service and maintenance of hydraulic equipment should be familiar with measurement systems used to identify particles by their size. The common units used are microns. 1 micron measures 39 millionths of an inch. Some particles whose size falls below the limit of human visibility, about 40 microns, require special techniques to detect and may include microscopic analysis and particle counting, already mentioned, using a machine that sends a laser through a sample to measure particles by refraction. To give examples of how small these particles may be, this slide lists comparative sizes of objects on the micron scale. To understand how well a filter can clean oil, you must understand this measurement system and how they're used by different rating systems. Let's first look briefly at filter media. Filter media can be designed to capture particles through two distinct methods: surface and depth retention. In surface retention, contaminants are held at the surface of the media. This provides an opportunity for the contaminant to become trapped as it comes in contact with the media surface. In depth retention, contaminants are held either at the surface of the media or within the labyrinth of passages within the depth of the filter media. This creates several opportunities for contaminants to become trapped. Either media type made may be used in conjunction with the rating systems we are about to discuss. The nominal rating refers to a filter capable of cutting off a nominated minimum percentage by weight of solid particles of a specific contaminant. Usually glass beads are measured to determine this. The specific contaminant greater than a stated micron size, normally expressed in micrometers, or 90% of 10 micron. It also represents a nominal efficiency figure, or more correctly, a degree of filtration. Process conditions such as operating pressure and concentration of contaminant will have a significant effect on the retention of the filters. Many filter manufacturers use similar tests, but due to the lack of uniformity and the reproducibility of the basic method, the use of nominal ratings has fallen into disfavor. The absolute rating, or cutoff point, of a filter refers to the diameter of the largest spherical glass particle, normally expressed in micrometers, which will pass through the filter under laboratory conditions. It represents the pore opening size of the filter medium. Filter media with an exact and consistent pore size or opening, thus theoretically at least, have an exact absolute rating. The absolute rating shouldn't be confused with the largest particle passed by a filter under operating conditions. The absolute rating simply determines the size of the largest glass bead which will pass through the filter under very low pressure differentials and non-pulsating conditions. This does not usually apply in practice. Pore size is modified by the form of the filter element, and it is not necessarily consistent with the actual opening areas. Furthermore, the actual form of the contaminants are not spherical, and the two linear dimensions of the particle can be very much smaller than its nominal one, permitting it to pass through a very much smaller hole, such as a cylindrical particle with a thickness less than the slot opening of the filter. The mean filter rating refers to the measurement of the average pore size of a filter element. It establishes the particle size above which the filter starts to be effective. It is determined by the bubble point test, and it is more meaningful than a nominal rating and, in case of filter elements with varying pore size, more realistic than an absolute rating. Until recently, there has not been a universally accepted test method to measure or describe the media pore size or the size of particles a filter media can capture and hold. Fortunately, now a test procedure called multi-pass testing or beta ratio testing is a universally accepted test method that yields readily comparable test results. It was introduced with the object of giving both filter manufacturer and user an accurate and representative comparison amongst filter media. Multi-pass testing uses a specific contaminant of known sizes added regularly in measured quantities to the fluid which is pumped continuously through the filter. Measured samples of the fluid are then taken at timed intervals, both the downstream and the upstream of the filter simultaneously. Particles are measured and counted by electronic means using an automatic particle counter. From these measurements, a beta ratio is formulated by dividing the number of particles of a particular size in the upstream flow by the number of particles of the same size in the downstream flow. ISO codes seen in the chart on the left are basically a three-number set, each number representing a particle size in microns and three different sizes. The code determines the set that you use. First is target cleanliness. The first step in setting your target cleanliness is to identify the most sensitive component in a system, or the most sensitive component supplied by a central reservoir. If the reservoir supplies multiple systems, the cleanliness is either determined by the needs of the most sensitive component, or the most sensitive component must be protected by a special isolated filter. For a recommendation of cleanliness code, see the chart on the right. These charts are also available from the manufacturer and should be consulted first when cleanliness targets are being developed. The most common form of oil filtration is full flow through a filter. In normal operation, all of the system's oil will flow through the filter media at this point. There is, of course, protection from full blockage by the bypass check valve, except for critical components such as proportional valves. In these cases, it is preferable that the oil flow be stopped to prevent damage to the valve. Since the valve is such a critical component of the hydraulic system, it must be equipped with some form of monitoring to ensure proper operation and protection. The filter housing should be equipped with indicators that will signal a need for maintenance or a filter in bypass. On today's sophisticated machinery, a pressure switch can be connected to a programmable logic controller whose instructions would dictate a course of action, such as shutting the machine down, setting off an alarm, or even texting a designated employee that there is a problem. On the most basic level, a filter should at least have a bypass indicator. Impurities in the compressed air, such as scale, rust, and dust, as well as the liquid constituents in the air which deposit as condensate, can cause a great deal of damage in pneumatic systems. These contaminants accelerate wear on sliding surfaces and sealing elements, adversely affecting the functioning and the service life of pneumatic components. As a result of switching the compressors on and off, pressure fluctuations occur, which have an unfavorable effect on the system operation. In order to eliminate these effects, compressed air preparation is needed. This slide shows what is being taken in by the compressor and compressed. Compression of the air causes heat buildup, and this in turn results in chemical changes in the air. The presence and location of the intake filter is critical, as it is the primary line of defense for pneumatic systems. Great consideration should be given to the location so as not to place a filter in an environment that will decrease its service life. In addition, the length of the intake piping on some systems is very long and must be sized correctly to reduce pressure drops. Filters should be easy to access. Contaminants are produced from any one of three sources. First, as the system is assembled, they may be built in as what happened in a dirty environment. Second, dirt can be generated when moving parts begin to wear. Third, dirt can be ingested by a filthy reassembly practice or through a seal in an actuator working in a dirty environment. In the Mid-South and to the East in North America, humidity levels in the air cause excessive buildup of moisture in the compressed air system. When the compressor takes in air, it is at a large volume, but then is compressed into a smaller volume. The humidity that existed in the larger volume is now in the smaller volume. Moisture in the compressed air system can cause many problems and must be removed. This process of moisture removal begins at the aftercooler. This device, as its name implies, is located after the compressor but before the receiver tank. Its principle of operation is that of condensation. The air coming from the compressor is hot and heavily humidified. As air enters the aftercooler, it is subjected to cooler temperatures, causing the moisture to fall out of the air and to collect in a section called the separator. Since air is lighter than water, the air moves up and out of the separator while the water remains and is ejected from a valve or other device that allows it to escape from the system. If moisture accumulates in a compressed air system, its effects can be devastating. First of all, the receiver tank is usually made of mild steel and is subject to rust and corrosion. Moisture will cause rust to accumulate in the receiver tank, and it will eventually dislodge and move downstream. Once in circulation, moisture will attack surfaces, including moving parts such as bearings and seals, and begin to wash away lubricants. Moisture will accumulate in cylinders, rendering the cushions ineffective, resulting in violent machine behavior and even possible failure. In addition to all these problems, moisture encourages the growth of bacteria and is a health problem. We will now look at some methods and places for capturing and removing moisture from the air system. The delivery system can be used to trap water vapor because the water is heavier than air. This illustration shows how water and air may be separated in a downward tilted delivery line by installing the machine takeoffs at points higher than the line itself. This method allows air to move upward while keeping the heavier water rolling downward to a point where it can be collected and removed from the system. There are two other methods of air drying that need to be discussed. These are chemical drying methods, such as using a desiccant or a deliquescent, and refrigeration equipment, which drops the air temperatures well below ambient. As the name implies, a refrigerated air dryer works by cooling down the air, like a refrigerator. The warm, wet air enters the dryer where it is cooled down to about 3 degrees Celsius. Since cold air holds less moisture than warm air, all water vapor that was in the air condenses into water. The refrigeration method severely drops the dew point in the air and provides extremely dry air. These examples use chemical action to remove moisture. First is the desiccant dryer. Compressed air to be dried flows through one tower, while the desiccant in the other is being regenerated. The purge air may also be heated, either within the dryer or externally, to reduce the amount of purge air required. The other type of chemical dryer is the deliquescent dryer. The moisture in the compressed air reacts with the absorptive material to produce a liquid that is drained out of the dryer. This effluent must be disposed of in accordance with local regulations. Learn more about deliquescent compressed air dryers and the differences it can make in your compressed air system. Airline filters, such as the one shown in this slide, are the last line of defense in a pneumatic system against contamination and moisture. While they are designed for trapping these contaminants, the presence of these at this point is a warning sign that there are problems upstream toward the compressor. The unit shown in the slide does three things. First, the component on the left is the filter and water trap. Any accumulated water may be drained from the polycarbonate bezel by manual or automatic means. The second component is the pressure regulator, which has been explained already, but whose job it is to reduce downstream pressure to limit needed by the equipment. The third component is the lubricator, which deposits atomized oil into the airstream for lubricating actuators and any equipment that needs oil. Lubricators are always needed, so you may find just a filter and a regulator. The operation of the airline filter is like any other filter, with the addition of a set of fins which cause air to spin at high velocity. At high velocity, the water molecules collect upon the sides of the bezel and fall into the bottom where they can be drained. This component should be inspected daily. Basic filtering elements may be classified as surface and depth, but air treatment requires further consideration. There are different types of air treatment components for removing contaminants such as solid particles, liquid water, water vapor and oil vapors, odorants, and even bacteria and viruses. For most automation applications, the focus is to remove solid particles and water. Water separators remove condensate either with a centrifugal design or a coalescing principle. A centrifugal separator causes a rotary motion in the air, forcing particles to accelerate in a radial outward movement. Once they reach the outside, they drain into the bowl. These are effective for removing water droplets as well as dust and dirt particles larger than 5 microns in size. No maintenance is required for this process. A coalescing separator flows from the inside to the outside of the filter element. These filter cartridges must be replaced regularly. Filters are used to remove particles, condensate, and oil. Coarse or particulate filters have a pore size of between 5 and 40 microns. The air flows past a centrifugal separator and then through the filter element. The filter elements are often a sintered material like polyethylene or bronze. Fine and microfilters remove particles smaller than 1 micron down to 0.01 microns. The air flows through the filter cartridge from the inside to the outside. Solid particles get stuck in the filter cartridge, clogging it up. Fluid particles such as condensate or oil coalesce or attach to larger droplets, which flow off and are caught in the filter bowl. It is important to cascade your filters to avoid prematurely clogging the filter element. For example, if a 1 micron filter is needed, it is recommended to use a 5 micron filter upstream so that the 1 micron filter does not become clogged with larger particles. A pneumatic lubricator injects an aerosolized stream of oil into an airline to provide lubrication to the internal working parts of pneumatic tools and to other devices such as actuating cylinders, valves, and motors. Airline lubricators usually contain the following parts: the head, an adjusting screw on the head, a bowl to contain the lubricant, and often a bowl drain to allow removal of the lubricating oil when needed. This is how the lubricator works. In the top of the head of typical airline lubricators, a small transparent housing can be seen. This housing will have an adjusting screw on the top. Turning that adjusting screw will increase or reduce the frequency of drops of lubricating oil that are being drawn into the airstream by the passing of compressed air through the lubricator head. The housing is transparent so that as you adjust the flow of oil via the flow adjusting screw, you can monitor the frequency of the lubricating oil drops as you adjust the flow. As the air passes through the lubricator head, the air path is reduced in size. This results in an increase in the speed of the compressed air through the lubricator head. In the narrow part of the lubricator head is an outlet for a small tube that extends from the head down into the oil inside the bowl. Air passing through the venturi inside the head creates faster moving air moving past the orifice to which the small tube is attached. This reduces the air pressure in the oil feed tube, creating a partial vacuum, and this vacuum draws oil from the bowl up the tube. The oil travels up the tube from the bowl, through the transparent housing, past the flow adjusting screw, and then drips back down into the airstream as long as the air is flowing through the lubricator. Depending on the style of the venturi and the speed of the air, the oil can be completely atomized or atomized to differing degrees. This atomized oil is carried out of the lubricator head in the compressed airstream and, providing the lubricator is placed close enough, downstream to the air tool or air component needing lubrication. Changing filters are a part of routine maintenance, and records should be kept to determine the best time to change them. When downstream pressure drops across filters are so large that machinery is affected, the time to change them has already passed. Pressure differential gauges are a good idea to monitor filter performance. Manufacturers specify filter performance to determine when pressure drops are excessive and require replacement of the element. Using specifications, we can determine the service life and set up an hour of operation schedule to change filters. Two of the most common air delivery systems used are grid and loop. The grid system is easy to install and often is selected when an existing facility is being utilized for compressed air operations. The chief disadvantage with the grid system is that long piping can cause pressure drops under heavy demand. Looping the piping has two effects. It equalizes the pressure drop because now the critical end use has at least two more diverse parallel paths to receive compressed air. And having a loop typically means the piping is the same size throughout the loop rather than reducing the size near the end. A typical plant that has not been well maintained will have a leak rate equal to between 10 and 30% of the total compressed air production capacity. The easiest way to identify leaks in a compressed air system is to walk the plant and listen for them, especially during non-production times. To estimate a plant's leak load, operate the air compressor in a load, no load, or start-stop mode during a non-production time. Record the loaded versus unloaded times and compare these to the compressor's capacity. One of the most common leak points in plants is at abandoned equipment. Consider adding an automated shutoff valve in the supply air line, which closes when the machine is turned off. Two methods of detecting leaks and equipment used to detect them are ultrasonic and acoustic detectors. Ultrasonic leak detection is the best way to find leaks in your air compressor system. An acoustic detector can recognize high-frequency air turbulence associated with leaks.